So another prime generating formula is actually the most important one of all. It's called the prime number theorem. So let me write it out. I think it deserves being written out. Really important result in mathematics. It's so important that you can refer to it by its TLA. You can refer to it by its three-letter acronym. Just call it PNT. People know what PNT is, the prime number theorem. It's that important. And the prime number theorem is about how many primes are there less than a number n. Right? So yeah, how many primes are there less than a billion? Something like that. And so the formula says that the number of primes less than n, well, the symbol for that is pi of n. Now, don't be confused. This pi is not 3.14. It's nothing to do with pi. We've reused the symbol for something else. So it's p for prime. So number of primes less than n. And this is approximately n divided by natural log of n. A couple of things to say, because some of you won't be familiar with that natural log of n. Some of you will. But for the ones who aren't familiar, I'll try and quickly show you. It's just a function. You could call it, it's just a thing. Any number. You pick a number. Any number like n can be written this way as a e to the power x. E is another constant. It's 2. I never remember what it is. 718 something something something. So any number can be written that way. It's 2.718 to the power of something, and the log of n is this bit. It's x. It's the power. So that's what log is. If I plot log of x, it looks like this. This is actually growing, but it grows really, really slowly. I think the log of a billion is 21. So yeah, you put in a big number and you're actually getting a very small number out. It's always getting bigger. It's actually tending to infinity. One more thing to say. This twiddle is a new symbol to you. Tilde, or twiddles as I like to call it, it's a new symbol. What it means is if you divide those two things, so I'm going to divide them like that. If you divide those two things, that's tending to 1 as n gets bigger. That's what it means. Slightly technical. You can say approximately equal to if you're happy with that, but that has a proper meaning. So what it's told us is tells us how many, on average, it gives us an approximation at least, of how many primes we can expect less than a number, a billion, 10 billion, a Google. But we can then get some results from that. That means that the proportion of prime numbers is, well, if we divide by n, the proportion of primes less than n is 1 over log n. So if we're talking a billion, I said the log of a billion was 21. So the proportion of primes is 1/21. It's like 5%. 5% of numbers less than a billion are prime. You can call it a probability if you want. If I picked a number at random, what's the probability that it's going to be a prime number? It's 5%. What does it mean? It does mean that the prime numbers are getting rarer, more spaced out as the numbers get bigger. So this proportion is getting smaller. The gaps, we can write the gaps as well. The average gap between primes is now equal to log of n. So if n was a billion again, let's stick with that. It turns out the average gap between the primes is 21. Some are bigger gaps, some have smaller gaps, some are twin primes, but the average gap is 21.
Let me give you a number, and you give me all the stats. I'll give you a number. Give me the state of the nation for the first 5.5 billion numbers.
5.5 billion. 5.5 billion is this. So a billion has 9 zeros, so this is 5.5 billion. We're going to take the log of that, the natural log. What have we got? 22.
22.4.
22.4.
So what do you now know?
So I know that the proportion of primes less than 5.5 billion is 1 over 22. Again, it's just like, well, let's see. Is it 4%? Let's see if we can do it. Yeah, so about 4% of numbers less than 5.5 billion are prime. The average gap is about 22.4, 22, 22, 23. So that's a lot of information. And then, one more thing we can learn from this. A prime number formula. The nth prime, twiddles, is approximately n lots of log n. So you might see where this comes from. If the average gap is log n, then you want to know the nth prime, you can multiply by n, you add the gaps all together. The nth prime is approximately n log n, which means 5.5 billion. The 5 billionth 500,000,000 prime is, it actually it's a better result the bigger the number is. So it helps you find, but it is an approximation rather than those prime number formula giving ones. One more thing I wanted to say about this, this average gap we've discovered was log n, and I said it was an average, so sometimes you get bigger than that, sometimes you get a twin prime, you make an average of it, you get log n. The gaps do have bounds on them. You can't go as big as you like. There's actually a little, it's called Bertrand's Postulate, and it says if you pick any number, let's pick the number n, he said that there will be a prime that is bigger than n and smaller than 2n. So you can't have a gap that is too big. There's a little rhyme for this. The rhyme is, Chebyshev said it and I'll say it again, there's always a prime between n and 2n. And if you put n as a prime instead, let's take it as the nth prime, then the next prime you're looking for has to be sandwiched between prime and 2 times the prime. Let's pick a prime. Prime's the nice version to do it. And what pick a prime?
11.
11's fine. Right, so let's have 11. All it's telling you is that you're guaranteed to have a prime between 11 and 22, which is true. So your gaps can't get too big. For primes over 100, you can do better than 2. That can actually shrink down to 1.2. So that gives you quite a narrow gap. So that just means that the primes can't have very, very, very long gaps between them. So they're quite regular. Primes are always turning up, they're fairly regular, and there's infinitely many of them, but they're like weeds. They're always popping up. You can't get rid of them. There's another prime. You don't go for too long without another prime popping up.
Surely when we get up into the sort of the Graham's numbers of the world, those weeds become a bit more sparse.
They become spaced out, but proportionally, compared to the size of numbers that you're using, the proportion is actually very, very tiny. In absolute terms, they're really spaced out. But as a proportion to these huge numbers we're talking about, they're close. This prime number formula is actually the easy version of the prime number formula. There's more sophisticated versions of this. They look the same, but they've added on extra terms. And so you can see that the error is sort of zigzagging around 0-ish.